Okay, this presentation is a quick overview of the Model 7156. My name is Bob Scandura, and let's get started. In this picture you can see the front panel connectors of the 7156, the analog and the digital connectors, as well as the PMC connectors on the back of the board. This is a block diagram of the board showing the major components. Two of the key features are the A to Ds, which are 400 megahertz 14-bit A to Ds. These are Texas Instruments ADS 5474s. And then also the DAC, which is a Texas Instruments DAC 5688. It's a dual channel 800 megahertz 16-bit digital to analog converter. One of the features of the DAC 5688 is it's an interpolating D to A converter. So while it has a maximum input sample rate of 250 megahertz, it can interpolate by a factor of 1 or 2 or even 4 or 8, getting you to the maximum 800 megahertz output sample rate. Another feature of the DAC 5688 is it's an upconverting D to A. So it can take a baseband frequency and it can convert that or frequency translate it up to a desired IF that can be chosen by the user. Another key feature of the 7156 is the timing bus generator. I'd like to take a few slides and explain how this works. The timing bus generator is based on a Texas Instruments CDC 7005. This is a clock synchronizer, a jitter cleaner. It has built-in dividers and clock distribution circuits. It allows us to provide a clock to the A to D section and a separate clock to the D to A section. And in one of the simplest modes, it takes an external clock from the front panel connector. In this case, a 400 megahertz clock would be appropriate because that's the speed or the sample rate of the A to Ds. And it would basically do a divide by 1 and send that out to the A to Ds on the board. But as I mentioned earlier, the D to As have a maximum input sample rate of 250 megahertz. So you take that same 400 megahertz clock, divide it by 2, and provide a 200 megahertz clock to the D to As on the board. Another clock mode involves using the timing bus connector. This is the multi-pin connector on the front of the board that has signals for clocking as well as gates and sync and trigger. In this case, we would take the same 400 megahertz sample clock, feeding it through the multi-pin connector through a ribbon cable, and then it would generate the 400 megahertz A to D clock and divide that down for the 200 megahertz D to A clock. Another clocking mode would be using the onboard VCXO, voltage control crystal oscillator. And this is a programmable VCXO. It can be programmed between 10 and 810 megahertz. In this case, again, the 400 megahertz would be appropriate for the A to D clock, which would get sent to the dividers. Divide by 1 would give you the 400 megahertz A to D clock, and a divide by 2 would give you the 200 megahertz D to A clock. Another feature of the CDC 7005 is the built-in synchronizer. So taking that same 400 megahertz VCXO frequency and sending that into the synchronizer, synchronizer also takes a 5 or 10 megahertz system reference clock, which would be sent to multiple boards, and it generates a VCXO feedback voltage to control the VCXO and keep it locked to the 5 or 10 megahertz system clock. That locked reference then gets sent into the divider circuits where, again, for the purposes of this example, we'll send out a 400 megahertz and a 200 megahertz A to D and D to A clock respectively. Now the way you'd use this in an actual application is you'd provide a single 10 megahertz or 5 megahertz system clock to the front panel connectors of all of the 7156s, and that would keep all of the A to D and D to A clocks on all of the boards synchronized with the 5 or 10 megahertz system reference. Up until now, I've been showing the CDC 7005 with 2 dividers. There are actually 5 on the board. We use 4 on the 7156. 2, as I've already explained, are used to generate the A to D and the D to A clocks. An additional 2 can be used to generate clocks that are sent back through the timing bus, and through a ribbon cable can be used to clock A to Ds and D to As on additional boards. The way you'd use this on a multi-board configuration is the first board would be turned on to be the bus master. Built-in circuitry would then drive through a cable connection, a flat ribbon cable, to the other boards on the cable. There's a terminator at the end that terminates those signals, and that allows you to have, besides the clocks, the gates, the syncs, the triggers, all of those circuits bust across multiple boards for a synchronized larger multi-board system. In the center of the 7156 are 2 FPGAs. The first is the processing FPGA, responsible for all of the data flows and board housekeeping, as well as doing any processing, either Pentec installed or customer created IP. The second is the interface FPGA, responsible for the PCIX interface, as well as being a second resource for doing processing on the board. The standard configuration is an SX50T, it's a Virtex-5 in the processing position, but it can be optionally upgraded to an LX155 or an SX95T or an FX100. These all give you options for more processing space on the FPGA. And the interface FPGA standard configuration is an LX30T, but that can be upgraded to an SX50T or an FX70T if you need more processing on that FPGA. Built into the 7156 are two banks of synchronous DRAM. These are DDR2 memories. The standard configuration gives you two 256 megabyte banks for a total of 512, or you can optionally get that larger to be two banks of 512 megabytes each for a total of 1 gig of synchronous DRAM on the board. These are used for either custom installed IP, where it might be a resource to the FPGA. They're also used with factory installed functions for data capture and playback. Let me show you those in a little more detail. The first mode would be data capture mode, where the A to Ds, full bandwidth 400 megahertz 14-bit A to D data, gets saved in the DDR2s, at which point then it can be read back through the PCIX interface to a host computer. The second mode is D to A playback mode, where data can be loaded through the PCIX interface into the synchronous DRAM, and then with built-in functions it can be played back either in one shot or continuously through the D to A's, producing an output at the RF outputs. For applications where additional I/O is needed to communicate with the FPGAs, option 104 installs the PMC P14 connection, and that provides 16 pairs of FPGA I/O to the processing FPGA and another 16 pairs to the interface FPGA. And many of our customers use these connections in their custom IP, and as configured from the factory, they're just simple read-write registers available in the memory map for accessing those pins. The 7156 operates as an XMC when the P15 connector is installed. This is called out as option 500, and it installs two 4x serial links to the FPGAs. Now these can be configured as two 4x links going to the processing FPGA, or one of those can be switched over to give you a 4x link to go to the interface FPGA. And typically each protocol requires a different reference clock, so the reason why we option it as a 5XX is when ordering we can put in the reference crystal you need for that interface. And some of those interfaces that customers install would be things like PCI Express and Xilinx Aurora as the serial fabric. Up until now I've been talking about the 7156 as a PMC module, but it's also available in other form factors. In each case we take the 7156 and we mount it on a carrier where it's tested and documented and sold as a single board set, which gives you the different form factors. And these include the 7256, which is a 6U compact PCI, the 7256D, which is the same 6U compact PCI but with two 7156s installed. There's a 7356, which is a 3U compact PCI, 7656, which is a PCIX board, which is useful in things like desktop PCs and blade servers. There's also a 7756, which is a full-length PCI Express form factor. 7756D is the same PCI Express, but with two 7156s installed on it. And there's also a 7856, which is a half-length PCI Express. And again, in each case, this is sold as a single board set, documented, tested, and basically operates as one board. Okay, I'd like to take the next few slides to discuss how applications are created for the 7156. Basically, all customers use Pentek's ReadyFlow BSPs or board support libraries to develop their applications. Included in the ReadyFlows are C language libraries, drivers that are specific to the operating system that's going to be used, application examples that can be used to get started or even to be the foundation for a larger application, and all the source code is included in the ReadyFlow libraries. The way we license it is that each developer requires a ReadyFlow package. Beyond that, there's no additional licensing. And the way it's sold is as a model 4994A156. That would be ReadyFlow for developers working in Linux. A 4995A156 would be developers working in Windows, and a 4996A156 are for developers who want to target VxWorks as their operating system. Pentec also offers development tools for doing FPGA design. These are sold as our Gateflow FPGA design kits. They're basically for customers who will be modifying the board's FPGA code beyond what is shipped from the factory. They include all of the FPGA code or intellectual property that provides all of the board's built-in functions, and they're provided to the developer as VHDL code. They may also include additional IP for functions like synchronous DRAM memory controllers or digital down conversion if those are part of the board's basic function set. We provide complete documentation and instructions for using Gateflow with the Xilinx development tools, the ISE Foundation tools. So a developer would take the Gateflow kit, open it as a project in the ISE tools, and then go on to expand that functionality for their own application, or maybe even replace it if it's appropriate for their application. The way we sell it is the 4953-156 Gateflow FPGA design kit. So, how do you get started using the 7156? Well, Pentec is offering a 7x56 developers bundle. It includes everything you need to get started. In the kit is the 7156 hardware, but again, that's available as a PMC or a 3U or 6U compact PCI or PCIX or PCI Express form factor, depending on what host you're going to be mounting it in. It includes a complete cabling kit for all the front panel cables as well as the timing bus cable for synchronizing multiple boards. It includes the development software in the form of the ReadyFlow BSPs, and those can be optioned either as Linux or Windows or VxWorks, depending on what target you're going to be developing for. It includes all the hardware and software documentation. It also includes lifetime product support, which is accessible through the telephone to talk directly to our application engineers, or through email, or through our knowledge base, and that's unlimited support. And the bundle represents a $2,000 savings off the price, or the total price, of all of the components in the kit. We're offering this until the end of 2009. So, what's next? Well, one thing you can do is visit the Pentec website at www.pentec.com. On the website you can find data sheets, manuals. We have a whole series of technology handbooks that not only feature our products but give you some of the foundation of the technology that's being used. You can also contact Mario Chavone, who is our sales manager. He can give you additional product information. He can give you a product quote. And you can also just discuss your application requirements with him and see if this product or any of our other products could satisfy those requirements. So thank you for taking the time to watch this, and hope you'll be using the 7156 soon.